Hi and welcome to a lesson of multivariable calculus. So in the first lecture of this lecture series, we talk about the functions of two variables and multivariable functions, and we find their domain and their range, and then we talk about surfaces and we talk about planes and lines, right? Now we are going to start a new topic, that is limits and continuity of multivariable functions. So let us recall for a single variable function, what we do in limit is that if we say that limit x approaches to a, f of x equals to L, then we say that L is the limit of this function at this point. It means that as the function is getting closer to and closer to the point A, so the function value is getting closer and closer to the point L, right? So similarly, in the case of multivariable, it is just extended. So we know that the domain is an ordered pair like this, x comma y. So this function and as this x comma y approaches a comma b, the function value approaches L. So we write L as the limit of the function, right? Now, we also know that sometimes in some cases limits may exist, and in some cases limits may not exist, right? So let's talk about this problem. For instance, if we have this problem that is limit x comma y approaches 2 comma 3, and the function is xy minus 2. So what does it mean is that, for instance, we can see it in xy coordinate system. So 2 comma 3 is, let's say it's a point on this Cartesian coordinate. Let's say this point here, 2 comma 3, right? So this is the point 2 comma 3. Now we can approach this point from various directions, right? We may approach it from here, we may approach it from here, we may approach it from here, and also we can approach from this direction or this direction, this direction. So there are infinite many directions that we can approach this point, right? So we have infinite many paths to approach this point. So if the limit L, we are representing this with L, if we approach this point in all directions from all paths and the limit is same in all paths, then we say that the limit exists. And if it's not the case that the limit is same in all paths, then we say that the limit does not exist. So now to find the limit of this function, what we need to do is just need to put this value of x and y into the function. So the value of x is 2, the value of y is 3 minus 2, so we get answer as 4. So the limit in this case is equals to 4. All right. Similarly, we have one more example here. We can see that xy approaches -1 comma pi, and the function is given. We just need to plug in the values of x and y, and we will get the limit as -pi. So a limit, we know that the limit -pi, and it exists, right? Now, in the case where we have indeterminate forms, if we recall in a single variable calculus, what we do was we use the L'Hopital's rule, or we use some a rationalization of functions to find the limits, right? Because indeterminate form is not sufficient to tell what's going on to the function, right? So we need to investigate further if we have this form. Similarly, in this multivariable function case, we also need to do something more to find the limit, right? So what we do is we approach at the point from different paths, and we see that either the limit is the same from all paths or not, right? So let's see what happens. We'll take some examples. Now, for instance, if we look here, this is the function, right? That is y over x plus y minus 1. Now what happens here is that if we apply this point 1 comma 0, so y is 0, so it's 0 over x is 1 plus y is 0 minus 1. So we get indeterminate form, right? Now this indeterminate form does not tell anything to us that the limit exists or not. So what we need to do is we need to check from various paths. So let's draw it on xy plane. Now this point 1 comma 0, it means that on the xy plane, it's let's say somewhere here, this is point 1 comma 0, so its x coordinate is 1 and y coordinate is 0. Now we can approach this point in various ways, right? For instance, we can approach this from this path where we can say y is equals to 0. We can approach this point from this path. So this is the line where x is equals to 1, right? So we may approach this point in different ways, and we can see that if the limit is same from these paths or not, right? Now, if we approach this point, let's say uh, from this line x equals to 1, now what we will get is limit uh, now x is 1, so we can say that x comma y goes to 1 comma y, and y over x plus y minus 1. Now this implies that y over x is 1 plus y minus 1. So this cancel out and we are left with y over y, which is equals to 1. Now if we approach from this way, that is the line x equals to 1, we get the limit as 1. All right, now we can approach from y equals to 0 and check whether the limit is same or not. So let's check that. So if y equals to 0, it means that it's 0 over x plus 0 minus 1, which means this whole function is going to be 0. Therefore, we can see that here we get 1 when we approach from the line x equals to 1, and we get 0 when we approach from the line y equals 0. So these limits are not same, right? So 1 and 0 are not equal. Therefore, we can say that the limit does not exist, right? You may think it as like in the case of a single variable function, we approach from the left and we approach from the right, right? Because it's a single variable function, we have a single variable x, so we can only approach from left or right, right? Since we have only one direction, one dimension, right? But in multivariable function case, we have infinite many paths to approach the point, right? So this way we can check the limit exists or not. Now let's see some more examples. For instance, now it's finding a simple limit, right? So now this is an example that limit xy tends to 2 comma 1, and this is the function, it's a rational function. So now if we apply these values here, that is 2 times 2 squared times 1 plus 3 times x is 2 and y is 1 over 5 times 2 times 1 is squared plus 3 times 1. Now this thing is equals to 14 over 13. So it's a defined value. So we say that the limit exists. So we don't need to check here uh, from different paths because the limit exists, right? It's not indeterminate form, but this is the determined form. It's a point, right? So we say that the limit exists and limit is equals to 14 over 13. Now let's take another example. Now see this example. This is the same as we did earlier. Now see this one. Now this is the example, that is x y over x squared plus y squared. and given that the point xy approaches 0, 0, now if we plug this point 0, 0, we are going to get the indeterminate form, that is 0 over 0. So now we need to investigate this limit from different paths. So first of all, we know that the point 0, 0 is the origin. So this is the origin, this point. Now we can approach this point from different path. Let's say we can approach from this path. That is, we can say this is y equals 0. We can approach from this path where we have x equals to 0. We can approach from this path as well, where we know that y equals to x, right? Because this also satisfies the limit 0, 0. Because if x is 0, from here we have y equals to x. Now if x is 0, then y is 0, so it uh, it satisfies, right? So now if we consider the limit along x equals 0, so what happened is that if we put 0 in place of x and then 0 and retain this y, we are going to get 0, right? Now for y equals 0, same thing happens, okay, but it does not guarantee that the limit exists, because we have already only checked with from two paths. So we say that we have infinite many paths, and we uh, have to check more paths, right? But it's not possible for us to check infinite many paths. So if you can show that from 2 or 3 paths that the limits are not equal, then we can say that the limit does not exist. Okay, so now if we plug y equals to 0 here in this function, we are going to get 0. Now if we approach from the line y equals to x, so now what happens here is that this is x times x over uh, x squared plus x squared. So we are going to get x squared over 2x squared. This cancels out and we get 1 over 2. Now if we apply the limit 0, 0 here, so again we are going to get 1 over 2, because this is a constant. So now we see that if we approach from the path y equals to x, we are going to get 1 upon 2, which means that these limits are not equal, where x is equals to 0 give us 0, y equals to 0 give us 0, and now y equals to x give us 1 over 2. So the limits in this case are not equal from the different paths, approaching from different paths. So we say that the limit does not exist, right? It is the same as we check in single variable function case. We only check from left and right there, right? So if the left hand side and right hand side limits are not equal, we say that the limit doesn't exist. So the same is the case here. If the limit from any two paths is different, then we say that the limit does not exist, right? Now let's take more problems. And now see here. Now we have a function that is xy squared over x squared plus y power 4, and again the limit xy goes to 0, 0, xy goes to 0, 0. Now if we apply 0, 0, we are going to get the indeterminate form. So again, it's not sufficient to give us some result, then we have to check from different paths. Now we know that the point 0, 0 is since this origin. Now again, we can approach from different paths, right? Now we can approach from different paths. It means that if we approach from x equals 0, we are going to get 0, right? If we plug 0 here, 0 times y squared over 0 squared plus y4, we are going to get 0. Again, we approach from y equals to 0, we are going to get 0. So for y equals to 0, this is going to be 0, right? So the function xy will approach 0. Now what happens if we approach from the line y equals to x? Now if we approach from y equals to x, this is what happens is x times x squared, and then x squared plus x power 4. So this is x cubed over x power 4 plus okay, so we can just take x squared is common, so we'll get 1 over x squared, and this cancels out, and we left with x over 1 plus x squared, right? Now if we put here limit x comma y going to 0 0, which means that we have to put 0 1 plus 0, so it's again 0, right? So again, now we get 0 from the path y equals to x, but again we can say that this is not sufficient to say if we are approaching from 3 or 4 different paths and the limit is same, so it's not sufficient to say that the limit exists, because there might be a different path from which we approach and the limit is not the same. So let's take one more path, that is, let's say we are approaching from this path, that is x equals to y squared, right? So we can approach from the path x equals to y squared as well, because the limit is 0 comma 0, and we know that if you plug x equals to 0, we get y equals to 0 as well. So this path is also favorable, right? So if we approach from this path, that is x equals to y squared, what we get is the function we have is xy squared. So here we get y squared times y squared over, for x squared we can write y squared whole squared plus y power 4, so it's y power 4 over y power 4 plus y power 4. So we have y power 4 over 2y power 4, which is equals to 1 over 2. Now if we apply the limit xy goes to 0 0, we are going to get 1 over 2. Now we see that from this path, that is from x equals y squared, we get the limit as 1 over 2, which is not equal to the previous limits where we get 0 0. So we can say that the limit for this problem does not exist, right? So the limit from different paths is not equal, so it's sufficient to say that the limit does not exist, right? So in this way we can see that the limit exists or not, and also we can see some more examples. So the next class we are going to see the continuity. So that's all for the time being. Thanks for watching the lesson.